An integral that has an infinite interval of integration, or that has a discontinuity within the interval of integration, is called an improper integral. So in this section, we're going to learn how to deal with these things. Remind me to verify some of these calculations on the calculator as we go. Okay, so a little warm up, evaluate some limits. So this is just a little Calc 1 problem. Remember that when you're calculating limits, the first thing you should try is to just plug the limit value into the expression. So if I want to take the limit as x approaches 2 of 7 over x minus 2, I try to plug the 2 in directly and I get 7 over 0, undefined. So you can't just plug in this case. So instead, we have to think about what happens when you plug in values closer and closer and closer to 2. So if you plug in, say, 2.1, 2.01, 2.001, what's happening to the value of the denominator? Smaller. The denominator is getting really, really close to 0. And when you divide 7 by numbers that are smaller and smaller and smaller, the value of that integral blows up, right? You divide 0.1 into 7, it's going to go in 70 times, right? But if you put 0.01 divided that into 7, it's going to go in 700 times. So it's going to get bigger and bigger and bigger, and this blows up to infinity. So when your denominator gets really small, the value of the fraction gets really big.
So anytime plugging in anytime at the limit before you can see 0, the denominator is just
0 in the denominator, yes, unless the numerator is also 0, and then you have to do some more work. Like L'Hopital's rule, if you remember that one. Okay, let's say I want to do, my expression is again 7 over x minus 2, but x is going to infinity this time. So my denominator is getting really, really big. Plug in bigger and bigger values of x, 10, 100, 1,000, a million, right? So 7 over a really, really big denominator is a really, really small value. It's getting closer and closer to 0. And then the last one, 7 over x minus 1. If I plug in 2, I can just put the 2 in and evaluate. So that turns out to be 7 over 1, or 7. So we're going to need to be able to take limits that look like these for today's lesson. Okay, so let's say I want to find the integral from 1 to infinity of 1 over x squared dx. So what does this represent? The bounds of integration, in general, a definite integral means the area under the curve, and the bounds of integration tell me from where to where. So this says from 1 to infinity, I want the area under this curve. Okay, so I want to know how much area is under that curve, starting at 1 and going to infinity. Okay, so this is a hard problem, right? Because we're dealing with infinity. How do you add up all that area? It goes on forever, right? So instead, what we do is we say, okay, first, let's just find the integral from 1 to b. We're going to have a stopping point. We're going to say, let's find the area from 1 to some point after 1. Call it b. So the integral from 1 to b of x to the negative 2 dx. Easier to use the power rule if I rewrite that as a negative exponent. So I'm going to increase the exponent by 1 and divide by the new exponent. So I have x to the negative 1 over negative 1, which just makes it negative. Evaluated from 1 to b. When I plug in a b, I get negative 1 over b. And when I plug in 1, I get negative 1 over 1. So I have 1 minus 1 over b is the area from 1 to some point in the future, b. So that integral represents the area under 1 over x squared from x equals 1 to x equals b. Now we're going to let b go to infinity. We're going to take a limit as b goes to infinity. So I'm going to fill in the blanks here. The integral from 1 to infinity of 1 over x squared dx. Instead, I'm going to integrate from 1 to b, 1 over x squared dx, and take a limit as b goes to infinity. So I already did this integral from 1 to b up above. It came out to 1 minus 1 over b. And now if I take a limit as b goes to infinity, what happens to the 1 over b fraction as b gets really, really large? It goes to 0. Yeah, that goes to 0. So this is 1 minus 0 or 1. Sorry about the little lines in there. That was a typo. It's just meant to be an empty box where you put the answer. So that's how you calculate an improper integral. Instead of going from 1 to infinity, go to 1 to some finite place b, and then take the limit as b goes to infinity. If I want to use a calculator to check our answer for this, I could integrate from 1 to 10, and then 1 to 100, and then even bigger, 1 to 1,000. And I could see, are my values of these areas getting closer and closer to 1? So your calculator can't do 1 to infinity because it would be calculating forever, but we can do 1 to any finite value. So I'm going to do math, function integration. I miss it, there it is, 9. Okay, so I'm going to go from 1 to 10 of 1 over x squared dx. I get 0.9. I'm just going to do the exact same calculation again, but I'm going to go from 1 to 100 this time. 0.99. Good. Maybe one more time. It might just turn it around to 1, you're right. 1 to 1,000. 0.999. Each time you add, each time you make the bound larger, it's going to take your calculator longer to do the calculation, but you be patient. It usually can come up with a number. So we have 0.9, 0.99, and 0.999. Those do seem to be approaching 1, which is the exact value that we calculated using a limit. So that's just a way to check your work when you're unsure if you did it correctly. Okay, so in general, if you want to integrate from a to infinity, instead you integrate from a to b, and then take a limit as b goes to infinity. Similarly, if you want to integrate from negative infinity to b, instead integrate from a to b and take the limit as a goes to negative infinity. If the limits exist, we say that the integral converges. In the last one, we got 1, so it converged to 1. But if the limit is infinite, we say the integral diverges. Sometimes there's infinite area under the curve that you're looking at. So here's another example. If I want to integrate from 0 to 1, 1 over 1 minus x to the 3/2 dx. So I've got a picture, and what I'm trying to find is the area under the curve between 0 and 1. So let's see if I can shade this. So the problem is that I have an asymptote at 1. My graph never actually gets there. It's closer and closer and closer. So as I get closer and closer to 1, I'm adding a little bit more area as I get closer and closer to 1. So I don't know if this converges. Is there infinite area or a finite amount of area? So the problem in this interval of integration happens at x equals 1. Everything's fine, but at 1, I have an asymptote. So instead of integrating from 0 to 1, where the problem is, I'm going to integrate from 0 to some random point b, right? 0 to b should be completely doable. It's just a fundamental theorem of calculus question. So I'm going to evaluate the integral from 0 to b. So first, I'm just going to rewrite this as 1 minus x to the negative 3/2. Then how do I integrate that? Yeah. Yeah, so the exponent rule and account for the chain rule. You also could write out a formal u substitution if you wanted, where you let u be 1 minus x. So I like that way better for simple ones, your way, rather than writing out the u. But feel free to write out the u if you don't know where the constant comes from that I'm going to write down. All right, so what happens is I'm going to increase the exponent by 1, so it becomes negative 1/2. Then you would divide by the new exponent, the negative 1/2, which is the same thing as multiplying by negative 2. But then I think I'm done, right? But I do a quick check by mentally taking the derivative of this in my head and making sure I get back to my integrand. So when I bring the negative 1/2 down and multiply by the 2, I get 1. Then I'd copy the 1 minus x, and I'd have negative 3/2. But then I'd have to multiply by negative 1 for the chain rule. So I need to get rid of that negative to make the chain rule work. So that is my antiderivative, 2 times 1 minus x to the negative 1/2. Like I said, do a u substitution if you don't understand why that's a positive 2 in front. And then what I have to do is evaluate that from 0 to b. So when I plug in b, I get 2 over the square root of 1 minus b. I just moved the negative exponent to the denominator and made the 1/2 power a square root. And when I plug in 0, I get 2. Okay, last step is let b go to 1. Because I don't want to integrate from 0 to b. I want to integrate from 0 to 1. So I'm going to take the limit as b approaches 1. So the integral from 0 to 1, this is my original integral. Instead, integrate from 0 to b and take the limit as b approaches 1. So this came out to 1 over square root of 1 minus b minus 2. And then I want to see what the value of this is as b approaches 1. So this fraction, as b approaches 1, the denominator is approaching 0. Right? And when a denominator approaches 0, the fraction gets big, right? So that is going to infinity. And infinity minus 2 is still infinity. So this integral diverges. The area under the curve from 0 to 1 is infinite. There's an infinite amount of area there. Okay, we'll do one more. We're not going to finish the whole thing. But if I wanted to evaluate this integral from 1 to 4 of 1 over x minus 2 to the 2/3 dx, where is the problem in the integrand? I've got a discontinuity in there. Where does it happen? At 2. Yeah, I can't put a 2 in there because I'd have a vertical asymptote at 2. So the problem is at x equals 2. Right? So instead of integrating from 1 to 4, I would integrate from 1 to b of 1 over x minus 2 to the 2/3 dx. And then I would integrate again from b to 4. So I'm kind of skipping over the problem spot. And then I'm going to take the limit of all of this as b approaches 2. 2. 2 to So that's the setup. We won't go through the whole finishing of the solving because we've done it a couple of times. I just wanted to show you how to set it up if the problem was in the middle instead of at the end.